Hello everyone. On behalf of the Department of Biomedical, Biological and Chemical Engineering at the University of Missouri, I welcome you to the 2021 Engineers Week. I'm going to present a pulse oximeter for the detection of silent hypoxia in COVID-19. This oximeter was designed and developed by our undergraduate students using the biophysical principles that we teach in the engineering curricula, with the assistance, of course, of faculty. What is a pulse oximeter? As the name suggests, it is a meter that measures oxygen saturation levels, and it also gives readings on pulse. It does so by clamping a finger with an optoelectrical device. It is non-invasive. The measurement takes only a few seconds and is reported in percentages, with 95% representing healthy. Blood oxygen level is clinically important because low oxygen can lead to organ failure as well as brain damage. So together with heart rate, blood pressure, breathing rate, and body temperature, it is measured and monitored as the fifth vital sign. Blood is oxygenated in the lungs. So if the lungs are not functioning properly, the oxygenation levels will be low. And it has been reported that up to 20% of COVID-19 patients have severe lung problems. And this sometimes manifests as silent hypoxia. Blood has a protein which is called hemoglobin. When hemoglobin has no oxygen, the blood looks purple or blue. Hemoglobin with oxygen, the blood looks red. So this differential absorption of light can be exploited to measure oxygen saturation levels in the blood. Below 90%, the blood looks purple and it becomes a medical emergency. For healthy, which is above 95%, blood looks red. So we use this principle to design a pulse oximeter. On one side, we have a light source, which is focused on a finger, and on the other side, we have a detector. So the light is transmitted through the finger and hits the detector. So why a finger? Fingers are rich in arterial blood, and they are also thin enough to absorb some light and allow some to be transmitted. The thickness of the finger changes with the cardiac cycle as the blood volume changes when the blood flows in and out. So that change of thickness with cardiac cycle manifests as a change in amplitude, which then gives us the heart rate. We have two sources of light, one infrared and the other red light. The infrared light helps us to remove other sources of absorption, to control for them. That is bone tissue, soft tissue, and other things. The saturation level is measured as a ratio, depending on the amplitudes of those two waves, signals. Our circuit is very simple. It consists of a LED control circuit, which controls the circuit, as the name suggests, and then the probe. The probe has light emission devices and a photodetector. The transmitted light is channeled to an amplifier filter circuit. The amplifier magnifies the signal that we get, whereas the filter circuit removes the noise from the external environment and from the other sources as well. This is then channeled to a computer interface. We've developed a user interface which is controlled by the LabVIEW software. and that's demonstrated on the diagram that is on your screen. And then we have also designed such that when the oxygen saturation levels reaches 90%, which is the clinically emergence, it gives off an alarm. And that's a close view of the individual components of our circuit. Thank you.
So this is our demonstration of the pulse oximeter. So here we have an example of the pulse oximeter created by our students here at the department. And we have it hooked up to the computer so that we can go ahead and see what's happening. So here in the first chart, what we can see is how much power we're sending to the LEDs. And this is important for us because we want to make sure we're sending the same power to both the infrared as well as the red LED in order to get an accurate measurement. Here in the second one, we have a measurement of the intensities that we are measuring after it goes through the skin, right? So we have the infrared denoted as white, and we have the red noted as red. And from this, we can measure the intensities of each one. And based off of those intensities, we can derive a ratio. So here we have our professor hooked up, and you can see that his blood oxygen level stays at around 96.7%, which is within the healthy range of 95% or above. And so if he holds his breath, so if you want to hold your breath now. So as he holds his breath, his blood's going to cycle through, and his blood oxygen level should start decreasing. And it takes a little bit of time for that to start happening. In the meantime, we can also see the beats per minute. So you can derive the heart rate from the widths here. And as he starts holding his breath, we should start seeing more of a difference between the red and the infrared, which is again going to indicate a larger ratio. And as such, it's going to change that blood oxygen level. Yeah, so here we can start seeing it become more drastic. And we see it decreasing, so it was at 96. Now it's going down to 95. And keeps going down. Yeah, so now it's under 95%, which, in most cases, under 95% could indicate that there's some type of issue that you would need to check, and it could be related to respiratory. And so now that he has stopped holding his breath, you can see it starts going back again to his normal average, which is around 97%. Yeah, thank you very much.